So thank you very much for having me here, Boris Grot. I will tell you a little bit about serverless, why it's really popular. No, it's not working. All right. Okay. Yeah, serverless, why it's important, popular, what the challenges are, and what we've been doing about it. So first of all, why serverless? So in order to understand that, let's kind of step back a bit and look at how cloud applications used to be traditionally deployed, which is basically as monoliths, right? So all of the logic packed into a powerful virtual machine, using lots of cores, lots of memory, things like that. The picture shows, a hypothetical online shop with some sort of a user interface, a bunch of mid-layer logic, maybe there's some accounting system or recommendation system, things like that, right? And then there's a data access layer in the back. And so traditionally, if you wanted to scale that, you would literally replicate that entire blob of stuff, right? Which is pretty fat. That's a difficult way to replicate things, especially if a performance bottleneck is just in one of these layers. Okay, so enter microservices. Enter microservices. And so microservices, as the name and the picture suggests, decompose that large blob of stuff into kind of natural constituent entities. You would have, the UI stuff would be, a standalone service, catalog its own service, recommendation system its own service, and so forth, right? And so what's really great about that model is that then you can, scale the individual services as necessary, right? So they're still running in virtual machines, but now these are leaner virtual machines that are much easier to scale independently compared to the original monolith, right? And so serverless takes this whole idea to the very extreme by decomposing the microservices into small independent units of work. Okay, so let's see, kind of a really quick overview of serverless. I actually expect most people, both here in person and online, already understand serverless, but so applications deployed to serverless run as collections of stateless functions. The functions are invoked on demand via some sort of a trigger. So it could be a function calling another function, the user, clicking a mouse, interacting through the browser, whatever. Functions are stateless, but applications are not, right? So there's still state, but it's externalized. So if a function needs to modify some state, it will access some sort of a storage service, database, object cache, that sort of thing. And what's really interesting about serverless is that all of the scaling, and I mean all of the scaling, all of the load balancing is handled by the cloud providers, okay? So, when we compare serverless deployments to standard virtual machines, a couple of key differences is that developers, don't really need to manage any of the infrastructure. That's fully offloaded to the cloud provider. So developers really love that bit. And the other interesting thing is that developers only pay for the actual runtime and the amount of memory used by the serverless functions. That is extremely different to the virtual machines, where the developers, or whoever runs the virtual machine, has to pay for all of the amount of time that the machine is up, right? So even if the VM is idle, you're still paying. Okay, so serverless is vastly different in that regard, right? And basically, as a result of this, the developers have a real financial incentive to reduce both the runtime and the memory footprint of serverless functions. Okay, now, the reason why cloud providers like serverless is because they get really high density and utilization at the server level, right? So they can pack a lot of functions on a single server, or they can have, some virtual machines and plug the gaps in the, couple of stranded cores or some amount of memory. They can plug those gaps with serverless functions. Okay, so what are the implications of this execution paradigm, right? So the good news, as already said, is tremendous deployment simplicity and the kind of advantage of the pay-per-use model. Now, it's not all great, the pay-per-use model, because per unit of work, it's actually much more expensive than virtual machines. But for some things, this is actually really, really beneficial. The bad news is basically really, really poor efficiency, right? The fact that the serverless functions are stateless means that there's a lot of communication. Communication is expensive in terms of latency. Using storage services may also be expensive. There's a phenomenal degree of interleaving across different functions that are co-located on the same server. We'll talk about that later. And there's also a lot of scaling due to traffic changes, right? So functions that are no longer used will be shut down, other functions will be launched, and all of this happens at really high frequency. And so cold start delays are problematic, okay? So, kind of problems in the real world are really good opportunities for research. But in order to do research, you need to be able to kind of dig in and play with the stack. And that is really difficult to do if, as a researcher, you don't own the stack, right? Every cloud provider has their own proprietary stack. You can use it, you can't change it. Okay, so how do we deal with that? And so in order to address this problem, several years back, we started a project that basically aimed to bring up the entire complete stack for serverless research, development, and deployment for that matter. So let's see. So essentially, the stack that we built, we call it vHive, is composed of a bunch of open source state-of-the-art components, right? So Kubernetes and Knative for cluster management, container management, and serverless function lifetime management. I apologize. A few of the animations will be slightly screwed up because this is a port from Mac to Windows. I'm still hoping that eventually Microsoft will get it right, but we're waiting for that day. Let's see. Obviously, containerd for containerization. We support two different types of micro VMs: Firecracker, which was originally developed by Amazon and then open sourced, and gvisor from Google, and Communication Fabric based in gRPC. Again, originally this was a Google project, now open sourced. And so we call that entire system vHive. Okay. Now, starting with the vHive as the core component of it, right? So that is the actual serverless stack. We, using that as an anchor, built an entire ecosystem for serverless research, benchmarking, instrumentation, and experimentation, right? So in addition to what I just mentioned, we have a bunch of performance analysis tools, like things for distributed tracing, microarchitectural measurements of serverless functions. We also have, okay, so it's had tremendous adoption for research, teaching, and so forth. In addition to this, we have developed and are continuing to develop and improve and augment a benchmarking suite. So we have about 35 or so standalone serverless functions. We call them micro benchmarks. They're completely standalone individual functions. And then we also have 8 complex applications, machine learning, training, inference, video analytics, data analytics, that kind of thing, okay? And then on top of all of that, we also have a bunch of these functions that are runnable as Gem5 compatible containers. Gem5 is a state-of-the-art full system simulator for architectural and microarchitectural research. So people doing hardware design can also run these serverless workloads, okay? So this is a screenshot of the web page for the vHive ecosystem. Here's the URL. So I very briefly covered, these 3 core components of vHive, but there's a lot more. Okay, let me highlight a couple of things. So one of these things that I want to highlight right now is what we call Stellar. So this is a tool for profile and benchmarking of actual cloud serverless frameworks. Okay, so at the moment we support 4 cloud providers. We have AWS, Google, Azure, as well as Cloudflare. Okay, and so this graph, again, I've taken it from a web page. The web page has plots different characteristics of these cloud providers. You can see, and again, that I'm absolutely not going to, highlight somebody or knock somebody. So this is not about judgments at this point. But at least what this graph shows is that AWS and Cloudflare have consistently, decently low median latency when it comes to cold invocations of serverless functions. So this is showing cold invocations, okay? Whereas Azure has much higher latency when cold functions are invoked, okay? Much higher latency. And in fact, you can see in this graph, there's kind of a blip blip on the right-hand side, you can see that on a particular day, for some reason, the latency in Azure for cold invocations considerably went up. Okay, so we've been doing this continuous profiling and monitoring for probably a good year or so at this point. So there's a lot of historical data that you can go and access. In addition to this, the tool itself is open source, so you can download it, tune it, and run it on your own cloud, like Huawei Cloud or whatever. Okay, another tool I want to highlight is something that is available kind of in a limited fashion, but we're about to release an absolutely major upgrade to it, and that is a tool called In Vitro. And what basically the problem that In Vitro solves is, how do you run a meaningful serverless load for any sort of research, analysis, understanding purposes, right? So if you're a cloud provider and you have your live serverless load, that is cool, but that is live traffic, right? And you have to be a hyperscaler in order to have access to something like that. So what do you do otherwise, okay? And so that is the problem we want to address. And so the way we address the problem is by combining several different components, right? So what we have is, first of all, we use real-world traces of actual serverless traffic released by the cloud providers. So these are simply invocation patterns with metadata like, you know, what was the function, how long, what, by what, I don't mean what the function did, but kind of like, you know, some function identifier, how long the function ran, how much memory it used. And so we take these traces, right? And then we have an entire tool chain that basically takes functions from our function suite with different inputs and so forth in order to map the little descriptors that are available in these industry traces to something that we can actually run, to a real runnable function, okay? And so then with, again, additional tools in this tool chain, we're able to subset that large industry trace to something much smaller, something you can run in a small VM, in a large VM, in a full server, on a cluster, right? So you can subset it to the size you need, right? And then there's a deployer that will basically, you know, use the subset trace and real functions that were mapped to the various instances referenced in that trace, and will run it on, you know, VM, server, cluster, or viewer choice, right? In a way, very accurately mimicking the load and running real functions in a way and with the same load that, you know, the cloud provider of whose trace is being used in this case observed in real time, right? So this is absolutely amazing as a research enabler. Okay, so that is a bit of the background, right? Again, this is kind of like the ecosystem that we've been developing. So I'll now walk you through one, and if time permits, two case studies of how we've been using vHive. So one case study I want to highlight is looking at the cold start problem. So Law Mind, his talk earlier today, he was talking about serverless, using serverless technology for LLMs, for LLM inference, and he highlighted the cold start problem in that context. Here we're looking at other use cases that are not LLMs, basically, right? And so again, the whole crux of the problem here is that as a user, you have no control as to if and when an instance of your function is available, right? And so when a request comes in, it may be the case that a brand new instance needs to be started, you know, booted up from scratch, and that takes time, right? And that is on the critical path of the request being served. So this is a problem. State of the art for tackling this problem is to use snapshots. So snapshots are well-known, well-understood technology. So what you do is you boot a virtual machine, you start the serverless function, right? And then just before actually serving the request, when everything is booted up and ready to go, you take a snapshot of the memory image, okay? And so then you can simply restore the function from that snapshot, essentially saving time on not booting the entire stack. Okay, so the question we're looking at is, the snapshot solve the cold start problem? Okay, so in order to answer that question, we need to look and see what exactly happens when a function is booted using a snapshot. So first, of course, there's a scheduler, which is really saying, hey, we need a brand new instance of this function. So there's a bunch of control plane action there. So that is essentially irrespective. That part of the stack is irrespective of whether the function being invoked is warm or cold, right? So that's just there. We're not concerned with that bit. After that, the two things need to happen. So a virtual machine monitor needs to be restored, right? And then the connections between that function instance and the control plane need to be restored. Okay, so two separate components. Now, I'm going to present in a minute a bunch of measurements that we did, for snapshot restoration, and we did these using the Firecracker micro VMs that are integrated into the vHive stack. And again, this is more or less the same kind of setup that you would get today in Amazon AWS. And then once all of this has been restored, right, so the VMM has been restored and connections to the control plane have been restored, function invocation can be processed. Okay, so here's a graph that basically compares the execution time, including the boot time, right, for a warm function instance and the cold instance that has been restored using snapshotting technology, again, originally released by AWS. So the x-axis shows a bunch of different serverless functions. Okay, for each function, there are two bars. One, which is on the left-hand side, shows the amount of time taken by the warm instance of that function. And so that's latency that is shown on the y-axis. And the right bar shows what happens when you restore that function from the snapshot. Okay. There are three components for each of the bars. There's the time to load the VMM, time to establish the connections. Of course, these don't apply to warm functions. Okay. And then the last component is the actual function processing. And that is the only thing that is there for a warm function instance. And as you can see from the graph, I mean, there is a huge difference on average, about 20x between function executing from a cold invocation versus a function that is 100% warm and ready to go when the invocation arrives. Okay. And so cold start delays are dominated by both connection restoration and, curiously enough, not the VMM loading part. That is exactly the delay that the cold starts, snapshots eliminate. But interestingly, function processing is a tremendous delay. And that is a very surprising result because, once a snapshot has been restored, shouldn't the function processing take exactly the same amount of time, from an image restored from a snapshot versus one instance? So what is going on? So the issue at play here is lazy paging. And lazy paging basically means that whenever memory is allocated, it is not backed by physical memory, right? And so in the context of snapshot restoration, lazy paging basically means that function image is loaded, there is virtual memory allocated, but for every individual page that is actually touched during execution, there's no backing physical memory when the snapshot has been restored. So that means that when we start running the function, every time we touch a brand new page of memory, that page needs to be paged in, right? And that happens in the critical path of execution, right? We start running, that memory is not actually there, right? So we need to bring in that page from, backing store, SSD over the network, whatever, right? And that happens for every single page until we brought in the entire working set of that function instance, right? And that is the thing that's killing the performance. Okay, so in order to kind of, understand what is really going on and, is there an opportunity to make the situation better, we performed the following study. So we trace page faults using a built-in Linux kernel tool called user fault FD. So it's a user space page fault handler. And we recorded the memory usage across invocations of the same function. Okay, and that is what I'm showing here. Okay. And so for every function, what I'm showing using these stacked bars is the number of pages. So the y-axis is the number of small 4 kilobyte pages that are either the same across invocations, and that is in blue, or completely unique at least in one of the invocations, And what you can see here is that, first of all, functions use a even like small short-running functions use a non-trivial amount of actual physical memory, right? So that is regardless of the VM size that I'm asking for, that is the actual physical memory, right? So up to about 100 megabytes per invocation. But the more important thing here is that the memory working sets of these functions are very, very stable across executions, right? What we can see is that up to 99% of all of the pages are the same across invocations, and that is considering the fact that the invocations are using different inputs, okay? And so those are the blue parts of the bar is, again, the pages that are consistent, the same across all of the invocations to the same function. Okay. And so this observation gives rise to the idea of recording the memory working set of these serverless functions and then replaying them back whenever the function is restored from a snapshot. Okay, and so we call our technique record and prefetch snapshots, or REAP. And that operates in two very simple and intuitive phases. In the first page, we record the working set, and we do that again using the userfault FD Linux kernel level utility. Once the pages are recorded, we write them into a very compact file that we call the working set file, and then we store it alongside with the actual snapshot, right? So this could be an SSD, this could be in an cloud object store, whatever, right? Sorry, I was supposed to have this animation here. Whenever the function is actually restored, right, we initiate the prefetch phase, right? So once the function is restored from the snapshot, in parallel with the starting to execute the function, we initiate this prefetching where we first read the working set file from the disk. The file tells us which pages are likely to be used because they were used in the previous invocation. And then we proactively restore all of these pages, allocating physical memory, populating TLB entries, and doing all of that stuff. Okay. Okay, and essentially the trade-off that REAP exploits is using a little bit of additional storage for the working set file that is actually quite trivial in order to drastically accelerate the call starts. Okay, so here's the key result here, right? So I'm going to go pretty easy on the graph. So this is sort of the only result graph I'll show for this portion of the talk. And as you can see here, so let's see. Again, same kind of graph I showed earlier. Again, two sets of bars, but the bars are now different. The bar on the left-hand side is what used to be the right-hand bar. So that is the baseline snapshots, okay? And the bar on the right-hand side is now REAP, right? Which is our record and replay prefetcher, right? And as you can see here from the graphs is that REAP significantly accelerates function processing by about 4.5x by eliminating approximately 97% of all page faults during the execution of the function. Now, the biggest benefit, of course, comes from accelerating the actual function processing by restoring the working set of the function. But interestingly enough, we find that even the connection establishment is also accelerated because we can bring in a bunch of useful pages that are part of the connection establishment protocol in the connection setup phase that happens as part of the snapshot restoration, VMI restoration. Okay, so kind of quickly summarizing this part of the talk, we discussed the fact that snapshots are a really effective way to accelerate call starts, but they suffer from the lazy paging problem. And so by recording and replaying the working set of the function being restored from the snapshot, we can make this process significantly faster. When we did this work and released the paper and the code, we were really pleased to find out that, Amazon actually integrated this work into their Firecracker, sorry, missing the right word here, whatever, repo. And so that was quite nice to have that happen. Okay, I will very quickly walk you through another use case where we used a bunch of the components of the vHive ecosystem to do something a little bit different, and that is looking at bottleneck understanding and elimination when it comes to warm serverless invocations, right? So before I was talking about cold invocations, now we're looking at warm invocations. So warm serverless invocations happen when the serverless function is actually, running, like it's actually been launched. It already ran at least once on a particular server. And in order to kind of dive into this work, let's first take a minute in order to understand what actually happens when serverless functions run on a server, right? What are the characteristics on a particular server? So first of all, the execution times of the functions are really short, right? Industry characterizations from different hyperscalers consistently show that in many cases, serverless functions have execution times on the order of a few milliseconds or even less. That is in stark comparison to, for example, running conventional workloads on a stock operating system like Linux, where a typical schedule in quantum is about 20 milliseconds. Right? 20 milliseconds turns out to be a good amount of time to amortize all of the overhead of context switching, right? So you have to page in a new process, right? You have to warm up microarchitectural structures, all of that stuff. So this is a really interesting challenge that arises because of this really, really short execution duration of serverless functions. Very small memory footprint, I already mentioned that earlier in the previous part of the talk, and relatively infrequent invocations. Now, the infrequent invocation part may come as a surprise, right? So why is it that functions are invoked, maybe once per few seconds, maybe even, once every few minutes? Why is that happening? So the reason comes back to cost, right? So serverless functions, getting a job done with serverless function per unit of work is considerably more expensive than doing the same thing on a virtual machine. And so in scenarios where there is a sustained load on a particular online service, it is simply not cost effective to run it on serverless, right? VMs are much, much cost efficient, right? So one would only want to use serverless for things that are relatively sporadic, relatively. And so that explains why the invocations are infrequent. Okay, the implications of this is that thousands of functions are resident on the server. Why? Because they take up little memory. We can pack a lot of them in, and they run for very short amounts of time. So we can afford a very high degree of interleaving. And so the interleaving thing basically means that between two invocations of the same functions, a lot of other functions will run in between. So what are the implications of this for the microarchitecture? Okay, so here I'm showing a graph that has two simple serverless functions. One is an authentication function written in Python. The other one is an encryption, AES encryption function in Node.js. I intentionally picked two different runtimes. So one is Python, the other one is jetted Node.js runtime. And what the axis shows is the interarrival time of the functions. I should mention something about the setup. So this is running on real hardware. So this is a real server that is experiencing a very high degree of interleaving across all of the different functions running on it. Okay, and so the y-axis shows the slowdown as a function, but not serverless function, of the interarrival time of the function under test in this scenario. Right, and what we can see is that kind of the portion of the curve on the right-hand side of the figure that is in this red highlighted box, this is interarrival times starting from about a second and up, which is the most typical range in real world scenarios, right? So that is the expected interarrival time. And as what we can see here, that in that range, functions experience a very significant slowdown, right? That's the y-axis here, compared to when they're executed back to back. That is to say, when the inter-arrival time is really, really small or negligible. Okay, so why is this happening, right? Why is there such a high degree of slowdown? The answer is interleaving, right? A function runs, then a lot of other things run. Those other things, those other serverless functions crash the microarchitectural state of the server, right? So the entire cache hierarchy, you know, the structures inside the core, you know, branch predictors, prefetchers, all of that stuff, right? So they're completely thrashed. And by the time the function runs again, it's basically as if it has just been cold booted, right? Like there's nothing on the CPU to help its execution, okay? And because it runs for such little time, it's not enough latency to amortize all of these structures getting warmed up. And so that is why, you know, these functions are experiencing a slowdown. Okay, so that's fine. Okay, so that is kind of like the high level clause. But if I actually drop down a bit and look at the microarchitecture, right? What is going on at the microarchitecture level, right? Are there certain aspects of this that are more prominent than others? Because if we can understand those aspects, hey, maybe we can actually propose some lightweight support in order to make this problem better, okay? So we did the study on recent generation Intel server. Here I'm going to show results for Intel Ice Lake. Okay, so a pretty modern server, 32 cores, you know, over 50 megabytes of last level cache. We use a bunch of different workloads written in different runtimes, 3 different types of programming languages, compiled, JITted, and interpreted, right? And we compare 2 scenarios. One is back-to-back, right? So that is the best case scenario. The function runs and then it runs again, and all of the microarchitectural structures are warm. And then the scenario with heavy interleaving, where a function runs once, then the microarchitectural state is essentially destroyed, and then the function gets to run again. So here are the results, okay? So here I'm highlighting 3 functions, AES, encryption, authentication, and a simple compute-intensive function, Fibonacci computation, in the 3 different languages that I mentioned earlier, Python, Node.js, Golang. And then on the right-hand side, the mean that shows the average results for all of the 20 functions in our benchmark suite. And then for each function, the 2 bars show, first of all, the back-to-back execution. Remember, that's the best case scenario. And then the second bar, the solid gray bar, shows the execution under the interleaving scenario. The y-axis shows absolute performance in cycles per instruction, where we obviously want as few cycles per instruction as possible, right? And think of this, when you look at the 2 bars side by side, higher is worse. So you can think of it as slowdown, okay? So what we find here is that interleaving drastically increases the CPI. In other words, it slows down the execution of the functions by anywhere between 100 and almost 300%, right? So it's a really, really significant performance hit, right? And again, this is at the microarchitecture level. So what is happening? So we run what is called top-down analysis, which is basically an analysis to try and identify the sources of the microarchitectural bottlenecks executing the instructions comprising a given workload, right? And there are 4 main categories here, right? At the bottom here, we have the category, so stacked bars, the bottom part of each bar is retiring the instructions. This is the good stuff. We want to be retiring instructions, right? We want all of the cycles to just retire. And we can see that that is a tiny fraction of the cycles. Everything on top of that are stall cycles. They're stalls, right? This is bad. We don't want our CPU to stall. Why are we stalling? There are 3 reasons. First is fetching the instructions, right? Now, fetching is a few things, but mostly it's literally getting the instructions, right? So if they're not in the instruction cache, we have to traverse the entire memory hierarchy until we find them either in another cache or maybe even in memory, okay? We have the speculation, so this is branch prediction and everything associated with that. And then we have the backend, which is, in this case, mostly dominated by accessing the data, again, from the memory hierarchy, okay? And so what we can see here is that the two main bottlenecks are what we think of as the front end of the processor. It's the branch predictor and the instruction fetch complex, okay? Together, these two things comprise 130 to almost 500% of the stall cycles in the interleaved execution, right? And of those two, the instruction supply part is really the dominant portion, okay? So if we can just focus on one and only one bottleneck, that would obviously be the bottleneck we want to go for. Now, I should add that we did the same exact analysis on two other generations of Intel servers. We looked at an older generation, Broadwell, and we looked at the most recent generation, which is Sapphire Rapids. Okay, I should say most recent as of maybe 6 months ago. And we see exactly the same trends. The absolute numbers change, the trends do not. Okay, and so specifically looking at the instruction part, what we find is that when we look at the last level cache, and I'll tell you in a second why we're looking at the last level cache, we find that for functions that are worn, there are very few misses in the last level cache, right? So we rarely need to go to main memory in order to find either instructions or data, okay? However, when we look at the interleaved execution, we find that we very frequently have to go to main memory in order to get both data and instructions, but particularly instructions, okay? So the y-axis in this graph shows MPKI, which stands for misses per kill instruction. So it's, you know, for every 1,000 instructions, how frequently do you need to go, in this case, to main memory in order to get either an instruction or a piece of data? Now, as you can see in this graph, the instructions are the bigger part of the problem. And not only are they more common than misses for data, but they're actually much more problematic. And the reason is that when we experience a miss for data, for a piece of data, for cache block, for data cache block, I should say, the out-of-order machinery of the microprocessor can hide a lot of this latency. However, when we cannot find an instruction in the instruction cache, the processor has no work to perform. It literally, the front end stalls, waiting for the cache block to come back. No instructions in the processor means out-of-order machinery is useless because, well, there are no instructions, right? So these misses are particularly problematic, right? Also, accessing memory takes literally hundreds of cycles. These are incredibly long latency stalls that are most problematic when we're talking about instructions, okay? So this is the main reason why warm invocations under high interleaving experience such poor performance, okay? It's off-chip misses, particularly for instructions. Okay, and so can we do something about this? Thinking in that direction, we analyzed instruction traces from, you know, a bunch of different functions that we've been working with, right? And we can draw two insights from our study. The first is that there's a very high commonality in the working set of instructions across invocations. Now, in the earlier part of the talk, when I was talking about snapshots, I was also talking about commonality. So that was the commonality was at the level of operating system pages, right? 4 kilobyte pages. Now we're talking about much finer granularity, which is instruction cache blocks. But again, it's not surprising that the commonality is there, right? A single function, even with a different input, will still go through more or less the same control flow. You will call the same set of, you know, subroutines, methods, and so forth, right? So it's not surprising that there's a lot of commonality across invocations of the same function. We also interestingly find that despite the fact that the functions, the serverless functions may execute for just, you know, perhaps a millisecond or a few milliseconds, they touch an enormous amount of code. They basically stream through code, right? They just stream through a lot of code, right? And so they go through almost up to a megabyte of code in a matter of milliseconds. I mean, it's really unprecedented if you look at our understanding of traditional workloads. Like, this never happens, right? So it's a really deep stack where a lot of code gets touched for very little time, and then execution moves on to a completely different portion of the code. And so this large instruction working set, because it's so big, it's impossible to preserve on the chip given the presence of a lot of functions that are interleaving at very fine granularity, right? So this is what's happening, right? By the time a function recurs, none of its code would be on chip. And that's why we have to go to main memory in order to get these instruction cache blocks, and that is what's giving the performance. And so spurred by all of these observations, we basically came up with the idea of recording and replaying. Again, I'm repeating the same concept as in the previous part of the talk, the instruction working set, but now this is happening at a much finer granularity, right? And therefore, we need a hardware technique in order to make this low latency and also transparent to the user of the system, okay? And so we developed this idea of a hardware prefetcher that during the execution of the function records the set of cache blocks, instruction cache blocks that are touched by the function during the execution. And then when the function is replayed, the cache blocks are restored into the cache hierarchy of the microprocessor. Now, I'll spare you the nitty-gritty kind of hardware and microarchitectural details of this technique, but the high-level sort of idea is, as I already said, recording and replaying instruction cache blocks associated with an execution of a function. We call this technique jukebox. Okay, so what we do is we record the misses in the second level cache of the microprocessor. We use a pretty compact spatiotemporal encoding, and we store this kind of trace of accesses in main memory. When the function is reinvoked in the future, the prefetcher will go through this metadata in main memory that says, hey, the following cache blocks have been touched, and it will proactively push them into the cache hierarchy of the microprocessor. I want to stress that the prefetcher is completely decoupled from the core. So it doesn't actually matter if there's some tricky control flow, some if then else statement where sometimes the if branch is taken and other times the else branch is taken. The prefetcher will just dump everything into the cache hierarchy, right? And then the core will find most of the cache blocks it needs near the core, right? Ideally in the second level cache, if not in the last level cache. The prefetcher records and replays virtual addresses. That means that if the operating system moves pages around in memory, nothing breaks. And also part of the prefetching is actually pre-populating the TLBs, again, by converting the virtual addresses to physical addresses as part of the prefetching process, right? So that's an additional benefit. Okay, so here is the main result for this part of the talk. So the x-axis shows, sorry, the bars show the baseline, and then kind of this proposed jukebox technique. The y-axis is the speed up, and in general, we see really good results across all of the benchmarks we study, with about 18% on average performance improvement, and roughly 85% or so of all off-chip misses for instructions being covered by the prefetcher. The prefetcher does need a little bit of metadata in memory, and that's only about 32 kilobytes in main memory of a serverless functions where, the amount of memory that the VM is using is maybe on the order of 100 megabytes or so, right? So this is nothing. I will add that we've done follow-up work where, in addition to restoring the instruction working set of the functions, we've also restored the branch predictor working set as well to further improve the coverage of the prefetcher. I'm not going to show the results, but again, we can improve the execution of these warm but rarely invoked functions even more. Okay, so that kind of brings me to the end. The meta point here is that all of this research has been enabled by the vHive serverless ecosystem that I introduced at the beginning of the talk. There's a really broad set of tools and a complete serverless stack that we've developed as part of this work. Yeah, and I talked about two techniques, one at the software level, operating system level, recording and replaying the pages of a snapshot in order to accelerate call invocations, and also recording and replaying microarchitectural state using a dedicated hardware prefetcher in order to accelerate warm invocations. There are a lot of people who have worked on this. This list is grossly incomplete because at this point we have a bunch of external collaborators who are also actively contributing. Yeah, the external list is particularly incomplete at this point. And I invite everybody to join our research community and use our toolchain. So we're very happy to help you guys, set up and get started. So that's it. Happy to take questions.